Did you know that the way we understand space, time, and gravity was completely transformed in the early 20th century? It all began with the theory of relativity, a groundbreaking idea from Albert Einstein that reshaped our entire view of the universe.
The theory actually has two parts: special relativity and general relativity. Special relativity, introduced in 1905, changed how we think about time and space, showing us that they're not as fixed as we once believed. Then, in 1915, Einstein expanded on that with general relativity, which explained gravity as the bending of space-time itself.
And here's the interesting thing. It's not just about the big stuff, like stars or black holes. Relativity actually plays a role in our everyday lives, too. It's behind the technology in GPS satellites, and it helps explain everything from the speed of light to the weirdness of time at high speeds.
Today, we're going to walk you through the history of how Einstein came to these conclusions, dive into the key ideas behind the theory, and talk about how experiments have backed it up. Plus, we'll look at how relativity influences technology and even pops up in movies and TV.
So, let's take a journey through time and space and see how one man's theories changed our entire understanding of the universe. Ready? Let's go!
To understand the theory of relativity, it's important to know how it all started. In the late 1800s, the prevailing view of physics was largely based on the work of Isaac Newton. Newton's laws of motion and gravitation were thought to describe the universe in its entirety. But as the 19th century came to a close, some puzzling observations began to suggest that there was more to the story.
The first big clue came from the work of scientists studying the behavior of light. The speed of light, they realized, appeared to be constant, no matter how fast the observer was moving. This didn't fit into the existing framework, which was based on the idea that all velocities should be relative. In other words, if you were moving toward a light source, the light should appear to be moving faster toward you, and if you were moving away, it should seem slower. But that wasn't the case. Light speed seemed to remain constant regardless of the observer's motion, and that was a mystery.
In 1905, Albert Einstein published a paper that would solve this puzzle. He introduced special relativity. Einstein's radical idea was that the speed of light in a vacuum is always the same, no matter the motion of the source or the observer. He also proposed that space and time were not absolute. They were relative and could change depending on the observer's motion. This was a revolutionary shift, and it led to the realization that time and space could bend in ways no one had ever imagined.
Einstein's theory was a game changer. It wasn't just a tweak to Newton's laws. It fundamentally altered our understanding of how the universe operates. For example, one of the key concepts of special relativity is that time doesn't always tick at the same rate for everyone. When an object moves at a speed approaching the speed of light, time for that object slows down relative to a stationary observer. This phenomenon is called time dilation, and it's been confirmed through numerous experiments, like those involving atomic clocks on fast-moving jets.
Alongside time dilation, another concept that came out of special relativity was length contraction. When an object moves at speeds near the speed of light, its length appears to shrink in the direction of its motion from the perspective of a stationary observer. These effects were mind-boggling at the time, and they challenged everything we thought we knew about the fabric of reality. Einstein's work in 1905 opened up a whole new way of thinking about the universe.
But that was just the beginning. In 1915, Einstein extended his ideas further with general relativity. While special relativity dealt with objects moving at constant speeds, general relativity tackled the more complicated issue of acceleration and gravity. The central idea of general relativity is that gravity isn't just a force acting at a distance. As Newton had thought, it's a curvature of space-time caused by mass and energy. Massive objects, like planets and stars, warp the space around them. And this curvature is what we experience as gravity.
General relativity also predicted some wild phenomena, like the bending of light around massive objects. This was confirmed in 1919 when a British expedition observed a total solar eclipse and found that light from distant stars was indeed bent as it passed near the sun. This discovery was one of the first major confirmations of Einstein's theory and caused a huge sensation. Suddenly, Einstein went from being a relatively unknown scientist to an international celebrity.
The theory didn't stop there. In the decades that followed, general relativity would continue to prove itself in more ways than one. From the prediction of black holes to the expansion of the universe, general relativity gave us new tools to understand the cosmos. In fact, the entire field of modern cosmology owes a great deal to Einstein's ideas.
The journey from Newton's laws to Einstein's theories wasn't smooth, though. Einstein faced a lot of resistance and skepticism from the scientific community when he first proposed his theories. But over time, his ideas were rigorously tested and confirmed, transforming the way we look at everything from subatomic particles to the vastness of space. Today, Einstein's theories are foundational to much of modern physics, and they continue to influence everything from technology to our understanding of the universe itself.
Now that we've covered the fascinating history of how the theory of relativity came to be, let's dive into the core concepts of special relativity. This is where things start to get really interesting, and let's be honest, a bit mind-bending. To understand special relativity, we need to wrap our heads around the idea that space and time aren't fixed. They can actually change depending on how fast we're moving.
Exactly, Tyler. One of the key postulates of special relativity is that the laws of physics are the same for all observers who are moving at a constant velocity. That means whether you're sitting in a car or speeding through space at 99% the speed of light, the laws of physics won't change. But the twist? The way we experience time and space does change depending on how fast we're moving. Sounds crazy, right?
Yeah, it's definitely a head-scratcher at first. But let's break it down. First, we have the speed of light. According to Einstein, the speed of light in a vacuum is always the same, no matter how fast the observer is moving. So, whether you're chasing light down the road or moving in the opposite direction, the speed of light remains constant. This was revolutionary because before Einstein, we thought speeds would add up the way they do in everyday life. If you're moving toward a light source, the light should look faster, right? Not with Einstein's theory.
And that's where time starts to get weird. If you were traveling close to the speed of light, time would actually slow down for you relative to someone who's standing still. This is called time dilation, and it's been proven in experiments involving atomic clocks. Scientists have shown that clocks on fast-moving jets tick slower than those on the ground. So, the faster you move, the less time passes for you compared to someone moving at a slower speed. Time isn't a constant, it's relative.
And this isn't just theoretical. It's a real effect that affects us in ways you might not expect. For example, GPS satellites, which orbit the Earth at high speeds, experience time differently from us on the ground. If we didn't account for the time dilation, their clocks would get out of sync with ours, and our GPS systems would be completely off. So, this crazy idea from Einstein has some very practical applications today.
But wait, it doesn't stop there. Another concept from special relativity is length contraction. When an object is moving at a speed close to the speed of light, it appears shorter in the direction of motion to someone observing from a stationary position. It's not that the object itself physically shrinks, it's just that the way we perceive it changes based on the relative speed. This one's a little harder to visualize, but it's been verified in experiments with fast-moving particles. The faster they go, the more their length contracts.
It's these kinds of ideas, time slowing down and lengths shortening, that make special relativity so fascinating. The fact that space and time are flexible, rather than fixed, completely shattered the previous understanding of the universe. It turns out that space and time are part of a single unified entity called space-time, and they can bend and stretch depending on your motion through it.
Yeah, space-time is the star of the show here. It's a four-dimensional fabric with 3 spatial dimensions and 1 time dimension. And just like how a heavy ball can stretch a rubber sheet, massive objects like planets and stars stretch space-time around them. This is where general relativity comes in, but that's a whole other mind-blowing topic we'll get into later.
For now, though, just appreciate how mind-bending it is that the faster you go, the slower time moves, and the shorter distances become. Special relativity completely changes how we think about the world, and it's still just as relevant today as it was when Einstein first introduced it.
And that's why this theory is so important. It isn't just theoretical. It affects how things work in the real world, from high-speed travel to how we understand the fabric of the universe itself. It's not just a physics lesson, it's a whole new way of looking at reality.
Now that we've wrapped our heads around the mind-bending ideas of special relativity, let's move on to the even more profound extension of those ideas. General relativity. While special relativity focused on motion and time, general relativity tackles the big question: how does gravity work? And as it turns out, gravity isn't quite what we thought it was. That's right. In Newtonian physics, gravity was understood as a force acting at a distance. Things with mass attract each other. But Einstein flipped that idea on its head. In general relativity, gravity isn't a force at all. It's the result of mass-bending space-time. Imagine space-time as a stretched-out rubber sheet. When you place a heavy ball on it, the sheet bends around the ball. This bending is what causes objects to move toward each other, not some invisible force pulling them in.
Exactly. So, instead of thinking of gravity as a force, we think of it as the way mass distorts the space and time around it. This idea was revolutionary because it meant that massive objects like planets and stars aren't just pulling on other objects with a force, they're actually warping the very fabric of the universe. And that curvature is what we experience as gravity.
One of the key predictions of general relativity was that light should bend when it passes near a massive object, like a star. This was a huge test for the theory. In 1919, during a solar eclipse, a team of scientists observed that light from distant stars was indeed bent as it passed near the sun. This was the first major confirmation of general relativity and a big win for Einstein. It was the moment when the world really began to take notice of his theories.
And this bending of light, which we now call gravitational lensing, is something we still observe today. In fact, scientists use it to study galaxies and black holes by watching how light from distant stars and galaxies is warped by the gravitational pull of massive objects. It's like using the universe itself as a magnifying glass.
General relativity also predicted the existence of black holes regions, where space-time is curved so much that nothing, not even light, can escape. And while we didn't have the technology to detect black holes in Einstein's time, today we have strong evidence that they exist. In 2019, scientists captured the first ever image of a black hole, which was a groundbreaking moment in both astronomy and physics.
And black holes are just one example of how general relativity continues to shape our understanding of the universe. The theory also plays a key role in understanding things like gravitational waves ripples in spacetime caused by massive objects like merging black holes. These waves were first detected in 2015, a century after Einstein predicted them. It's a perfect example of how his ideas have shaped the science of today.
And that's not all. General relativity is used in practical technologies too. Take GPS systems, for instance. The satellites that provide GPS data are moving fast enough and are far enough from Earth's gravitational pull that they experience time differently from us on the ground. If we didn't account for the effects of both special and general relativity, our GPS systems would be off by miles. So, even though it's a concept that sounds purely theoretical, relativity is essential to the technology we rely on every day.
It's incredible, isn't it? General relativity not only redefined our understanding of gravity, but also gave us tools to explore and understand the cosmos in ways we never imagined. It's a theory that continues to shape the cutting edge of science, and who knows what new discoveries are still to come from it.
For now, we've only scratched the surface of what general relativity can teach us. From black holes to the expanding universe, Einstein's theory continues to open new doors in physics. And that's exactly what makes it one of the most enduring and revolutionary ideas in science.
Now that we've covered the core ideas of general relativity, it's time to talk about how we know it's true. It's all well and good to have a brilliant theory, but in science, theories are only as strong as the evidence that supports them. Fortunately, Einstein's predictions were put to the test and have been repeatedly confirmed by a series of landmark experiments.
Exactly. One of the first major tests of general relativity came just a few years after Einstein published his theory, during a solar eclipse in 1919. British astronomer Arthur Eddington led an expedition to observe the bending of light as it passed near the sun. According to general relativity, light from stars that passed close to the sun should be bent by the sun's gravity. The results were nothing short of spectacular, Eddington's team observed exactly the kind of light bending that Einstein had predicted. This confirmed the theory and made Einstein an international celebrity.
The 1919 eclipse observation was a huge moment in science, but it wasn't the only experiment that supported general relativity. In fact, the theory has continued to stand up to rigorous testing ever since. For example, in the 1970s, scientists began to test the effects of general relativity more precisely with the help of satellite technology. They used atomic clocks aboard satellites to measure the effects of gravitational time dilation, the idea that time moves slower the closer you are to a massive object. And guess what? The clocks on satellites, far from Earth's gravitational field, ticked faster than those on the ground, just as Einstein had predicted.
And then there's the amazing case of the GPS system. I know, we're all familiar with how GPS works to help us get from one place to another. But did you know that it's based on principles from both special and general relativity? Because satellites are moving at high speeds and are further from Earth's gravity, the passage of time is different for them compared to us down here on the ground. If scientists didn't account for both time dilation and gravitational time effects, our GPS would be off by miles. It's a real-world example of Einstein's theories at work in everyday life.
Absolutely. It's crazy to think that without general relativity, we wouldn't have accurate GPS. Another key test came in the 1990s with the discovery of gravitational lensing. As we mentioned earlier, general relativity predicts that massive objects like galaxies should bend the light from more distant objects behind them. Scientists have observed this effect in action, and it's given us a way to study things like black holes and distant galaxies. Gravitational lensing has become an essential tool for modern astrophysics, helping us see the universe in ways we never could before.
And let's not forget about one of the most exciting discoveries in recent years, gravitational waves. Gravitational waves are ripples in space-time caused by massive objects, like black holes or neutron stars, colliding or merging. These waves were first predicted by Einstein a century ago, but it wasn't until 2015 that we detected them for the first time. This discovery, made by the LIGO experiment, confirmed another key prediction of general relativity and opened up a whole new way of studying the universe.
Gravitational waves were such a big deal that the team behind the discovery was awarded the Nobel Prize in Physics in 2017. The fact that we can now measure these tiny ripples in space-time is nothing short of mind-blowing. It's like we're hearing the faint echoes of cosmic events that happened billions of years ago. It's a whole new era of astrophysics, and it all comes back to Einstein's theories.
All of these experiments, light bending, time dilation, gravitational lensing, and gravitational waves, serve as powerful confirmations of general relativity. Each one of them tests a different aspect of the theory, and each time it's held up under scrutiny. It's pretty incredible to think that a theory developed over a century ago is still being tested and proven true today.
And it's not just about proving Einstein right. These experiments and observations have expanded our understanding of the universe in ways that we couldn't have imagined. Thanks to general relativity, we now have tools to probe deep into the cosmos, study black holes, measure the curvature of space-time, and even detect events across vast distances. It's a testament to how powerful and enduring a theory can be when it's grounded in such solid evidence.
Now that we've gone over how Einstein's theories have been proven through experiments, let's dive into two of the most mind-blowing aspects of special relativity: time dilation and length contraction. These effects are among the most famous and often misunderstood predictions of the theory. So, let's break them down.
Time dilation is probably the more well-known of the two, and it's exactly what it sounds like. Time moves differently depending on how fast you're going. The faster you travel, the slower time moves for you compared to someone who is stationary. This might seem totally counterintuitive, but it's been confirmed by countless experiments. For example, scientists have shown that atomic clocks on airplanes actually run slower than those on the ground. And when you bring those clocks back, the difference in time is noticeable.
Yep, time slows down when you're moving at high speeds. But here's the catch. It's not that time is literally slowing down for you, it's relative. So, from the perspective of someone on the ground, it would appear as though the person on the moving airplane is experiencing time more slowly. But from the perspective of the person on the plane, everything feels normal. It's only when the clocks are compared afterward that we see the difference.
And this isn't just some quirky idea you can ignore. The effects of time dilation have real-world implications. For instance, astronauts traveling in space at high speeds would experience time more slowly than people back on Earth. If they took a trip to a star and came back, they would have aged less than the people who stayed behind. This has actually been tested with particles traveling at high speeds in particle accelerators. They last much longer than they would have if they were just sitting still, thanks to time dilation.
That's right. But time isn't the only thing affected by speed. There's also length contraction, which is another fascinating effect of special relativity. In short, the faster an object moves, the shorter it appears in the direction of motion. From the perspective of an observer who is stationary, it's like if you were zooming across the galaxy at near light speed. The spaceship you're in would seem squished, even though it's perfectly normal to you inside.
Right! And just like with time dilation, length contraction only happens when you're moving at extremely high speeds near the speed of light. For everyday speeds, the effect is so tiny it's practically undetectable. But the closer you get to the speed of light, the more pronounced it becomes. In theory, if you could travel at light speed, the length of your spaceship would appear to shrink to zero. But, of course, according to Einstein, you can't actually reach the speed of light if you have mass, because it would require infinite energy.
It's one of those things that seems so strange at first, but once you start to understand how relativity works, it makes more sense. These effects, time dilation and length contraction, are directly tied to the idea that space and time aren't fixed. They're part of the same fabric space-time, and they bend and stretch depending on your motion through it.
Exactly. And while these effects sound incredibly strange, they've been confirmed again and again in experiments. Take, for example, the famous twin paradox. Imagine one twin stays on Earth while the other goes on a journey to space at near light speed. When the spacefaring twin returns, they'll be younger than their sibling who stayed behind. It's not that one twin aged slower on purpose, it's just that time moves differently when you're moving at high speeds.
These two effects, time dilation and length contraction, are at the heart of what makes special relativity so revolutionary. They fundamentally challenge the way we perceive time and space in everyday life. And the fact that they've been experimentally verified so many times speaks to just how accurate and powerful Einstein's theories are. It's no longer a matter of what if or maybe. It's proven science, and it has some pretty profound implications.
Definitely. And these effects aren't just theoretical. They have real-world consequences, especially as we continue to explore space and develop new technologies. Understanding time dilation and length contraction not only expands our knowledge of the universe, but also gives us the tools to make practical, everyday technologies work even better. So, even though these concepts may sound like science fiction, they're very much grounded in the science of today. Now that we've covered the mind-bending effects of time dilation and length contraction, let's talk about one of the most famous and mysterious predictions of general relativity: black holes. These are regions of space-time where gravity is so intense that not even light can escape. They're a natural consequence of Einstein's theory, but their discovery and study have led to some of the most fascinating questions in modern physics.
Black holes are really the ultimate test of general relativity's predictions. According to Einstein, when a massive star runs out of fuel, it can collapse under its own gravity, creating a singularity, which is a point in space where density becomes infinite and space-time curves infinitely. This forms a black hole, a region so dense and compact that it warps space-time to the point where escape is impossible. Once something crosses the event horizon, the boundary around the black hole, it's gone, and nothing, not even light, can get out.
That's what makes black holes so captivating. They're invisible. We can't directly observe them because no light escapes, but we can detect their presence through the way they interact with the matter around them. For example, when a black hole pulls in gas and dust, the matter heats up as it falls toward the event horizon, emitting radiation that we can detect with telescopes. This has allowed us to identify black holes in distant galaxies and even measure their size and mass.
And we're not just talking about tiny, isolated black holes. There are supermassive black holes at the centers of most galaxies, including our own Milky Way. These giants can be millions or even billions of times more massive than the sun. It's amazing to think that something so massive can exist in the center of a galaxy, and it's still mind-blowing how their immense gravitational pull governs the movement of stars and entire galaxies.
One of the most fascinating features of black holes is their ability to warp space-time. According to general relativity, mass and energy bend the fabric of space-time around them, and black holes are an extreme example of this. The closer you get to a black hole, the more extreme the bending gets, eventually leading to a singularity, where the curvature becomes infinite. It's almost like space-time gets folded in on itself.
It's mind-blowing to think about how space and time behave near a black hole. If you were to fall into one, time would seem to slow down for you from the perspective of an outside observer. And as you approach the event horizon, the stretching of space-time would become more extreme. In theory, if you could survive the journey, which you wouldn't, your perception of time and reality would be completely warped by the black hole's gravity.
And yet, despite how strange and terrifying black holes are, they've been confirmed again and again by both theory and observation. In fact, in 2019, scientists captured the first ever image of a black hole's event horizon using a technique called the Event Horizon Telescope. It was a huge milestone and an incredible confirmation of Einstein's theory, showing us what a black hole actually looks like, well, sort of. It's more of a shadow since the black hole itself is invisible.
That's right. The image itself showed a bright ring of light surrounding a dark center, which was the black hole's shadow. This groundbreaking image has opened up new avenues for studying black holes and has given us an even deeper understanding of the role they play in the universe. And even though we can't observe the inside of a black hole directly, the effects of their gravitational pull are everywhere around us.
Black holes are more than just cosmic oddities. They're essential to our understanding of space-time and gravity. They stretch our imaginations and challenge our understanding of the universe. And despite their bizarre nature, black holes are one of the most solid pieces of evidence supporting general relativity. As science progresses, we're bound to learn even more about these strange objects and perhaps uncover even more mysteries about the nature of space and time.
So now we've covered some of the coolest and most mysterious aspects of general relativity. But let's take a step back and look at how it's impacted modern physics. The theory of relativity, both special and general, didn't just add to our understanding of the universe. It completely reshaped the foundation of modern physics. It changed everything, from how we understand gravity to how we study the cosmos and even particles at the smallest scales.
Exactly. When Einstein's theories were first introduced, they were groundbreaking. But what's so fascinating is how they continue to shape the way we think about the universe today. Relativity has influenced not only astrophysics and cosmology, but also the development of quantum mechanics and the ongoing search for a unified theory of physics. In a way, Einstein set the stage for all the physics that came after him.
One of the major impacts of general relativity was on our understanding of gravity. Before Einstein, Newton's laws of gravity were the go-to model. They worked perfectly fine for most things, but they were limited. Einstein's theory took that understanding further by revealing gravity as the warping of space-time itself, not just an invisible force. This new model has been essential for understanding everything from the motion of planets to the dynamics of galaxies and even the expansion of the universe.
And that's not all. General relativity also pushed forward the study of black holes, dark matter, and dark energy, some of the biggest mysteries in modern physics. Without Einstein's ideas, we wouldn't have the theoretical framework to even begin looking at things like supermassive black holes or the strange phenomena we observe in the outer reaches of the universe. His theory opened the door to a whole new world of questions, and physicists are still trying to answer them.
It's not just the really big stuff, either. Relativity has had a huge influence on the development of particle physics, particularly in how we understand space and time at the quantum level. For example, the relationship between energy and mass, expressed by the famous equation, E = mc squared, has had profound implications for everything from nuclear energy to the creation of matter and particle accelerators. This equation underpins some of the most important discoveries in modern physics.
Another area where relativity plays a crucial role is in the study of the early universe. The Big Bang theory, for instance, relies heavily on general relativity. The concept of an expanding universe, which was proposed by Edwin Hubble and later refined by others, is based on the idea that space-time itself is stretching, as predicted by Einstein. In fact, the entire field of cosmology is built upon the foundation that Einstein established with his theory of general relativity.
Relativity also has profound implications for modern technology. Beyond GPS, which we already mentioned, another example is the way relativity is used in high-energy physics experiments, like those at CERN. When particles are accelerated to near-light speeds, their interactions and behaviors must be understood using relativity. Without accounting for relativistic effects, the experiments wouldn't work as they do, and we wouldn't be able to study things like the Higgs boson with the precision we have today.
And, of course, we can't forget how relativity plays a role in our understanding of time itself. The more we study relativity, the more we realize that time isn't this fixed, unchanging concept. Time can stretch, bend, and slow down, depending on how fast you're moving or how close you are to massive objects. This shifts our entire perspective on the universe and how we experience reality itself.
It's amazing to think that a theory first proposed over 100 years ago is still one of the cornerstones of modern physics. Whether it's guiding the study of black holes or impacting the way we use technology, relativity continues to shape how we explore the universe. And as we develop more advanced tools and techniques, it's likely that Einstein's theories will continue to guide us toward even more discoveries.
Absolutely. Relativity didn't just change the way we understand space and time, it changed the way we think about the universe itself. And as science continues to progress, there's no telling how many more mysteries we'll uncover thanks to the foundation Einstein laid. What we do know is that his work will remain central to our understanding of the cosmos for years to come. Now that we've covered the groundbreaking impact of general relativity on modern physics, let's take a look at some of the critiques and misunderstandings that have come up over the years. Like any revolutionary theory, general relativity faced and still faces its fair share of skepticism, and some of the ideas in the theory are still tough to wrap our heads around even today.
That's right, Monica. One of the biggest challenges is the way general relativity treats gravity. It's such a departure from how we've traditionally thought of gravity as a force acting across space. Instead, Einstein's theory tells us that gravity is a result of the warping of space-time. While this is now well established, it's still difficult for many people to grasp the idea that mass doesn't just pull objects, but actually changes the very fabric of space and time itself.
Exactly, and this concept of curved space-time can feel pretty abstract, especially when you try to imagine it. I mean, trying to visualize a four-dimensional space-time fabric bending around a massive object like a star is no easy task. And while mathematicians and physicists use equations to describe these curves, the idea can seem almost like science fiction to the average person, despite being backed by strong evidence.
Another big criticism that general relativity faced early on was its complexity. Einstein's equations are notoriously difficult to solve, especially in more complicated scenarios, like when you're dealing with objects that are moving at high speeds or in strong gravitational fields. The math required to predict what would happen near black holes or during the Big Bang was beyond the capabilities of early 20th century scientists. Even today, we still don't have complete solutions for every scenario the theory predicts.
And even though general relativity has been confirmed through a lot of experiments and observations, there are still aspects of the theory that scientists are trying to understand more fully. For example, general relativity doesn't mesh well with quantum mechanics, which governs the behavior of particles on the smallest scales. These two pillars of modern physics, general relativity, and quantum mechanics, don't quite fit together, and finding a theory that unifies them has been one of the biggest challenges in physics for over a century. This is where things get really tricky.
Right, and this discrepancy between general relativity and quantum mechanics is often referred to as the problem of quantum gravity. While both theories have been spectacularly successful in their respective domains, they describe nature in fundamentally different ways. General relativity views space-time as a smooth, continuous fabric, while quantum mechanics suggests that at the smallest scales, space-time could be grainy or quantized. Physicists are still working on a theory like string theory or loop quantum gravity that could bring these two together.
There are also some common misconceptions about relativity that have popped up in popular culture. For example, people often hear about time dilation and think that it means time literally stops for someone traveling at near light speed. But that's not quite right. From the perspective of the person traveling at that speed, their experience of time feels completely normal. They wouldn't notice any difference. The slowing down of time is only seen by someone watching from a stationary position. It's a subtle but important distinction.
Yeah, it's easy to get caught up in the sensational side of relativity, but when you look at the real science behind it, things like time dilation and space-time curvature make perfect sense in the context of the theory. And while the concepts can be mind-boggling at first, once you start to understand how space and time are interconnected, it all begins to click. Still, there's no denying that some of the more advanced implications of general relativity can be hard to accept or visualize.
That's part of what makes Einstein's work so impressive. He didn't just challenge our understanding of gravity and motion, he gave us a whole new framework for thinking about the universe. And even though some parts of the theory are still hard to grasp or resolve, the core of general relativity has stood the test of time and experimentation.
And that's why general relativity is still one of the most important theories in physics today. It's a theory that continues to evolve as new discoveries are made, and it's the foundation for a lot of the work being done in cosmology, astrophysics, and beyond. Sure, it's complex, and it has some parts that are still being worked out, but that's what makes it such an exciting field of study. The more we understand, the more we realize just how much we still have to discover. Now that we've covered the theory itself, let's switch gears a bit and talk about how relativity has made its way into popular culture. Einstein's theories have inspired countless films, books, and TV shows, often influencing how we think about time, space, and the nature of the universe. It's fascinating how his ideas have permeated not just the realm of science, but also the creative worlds of science fiction and beyond.
Right? Relativity has become a sort of shorthand for futuristic, mind-bending concepts in pop culture. One of the most iconic examples is the Back to the Future franchise. The concept of time travel is central to the films, and while they take plenty of creative liberties with the science, they do touch on aspects of relativity. For example, in the first movie, Doc Brown explains how traveling at speeds close to the speed of light would allow you to jump through time. While the exact science is a bit of a stretch, the connection to Einstein's theories is clear.
Absolutely. And then there's Interstellar, a movie that takes relativity even more seriously. Directed by Christopher Nolan, the film dives deep into the effects of gravity on time. In one scene, the characters visit a planet near a supermassive black hole, where time moves much slower due to the intense gravitational pull. This is a perfect example of time dilation, and it's portrayed very accurately given the limits of Hollywood storytelling. The filmmakers even consulted with physicist Kip Thorne to make sure the science was sound.
Interstellar isn't the only film to feature black holes and gravitational time dilation. Another great example is The Theory of Everything, the biographical film about Stephen Hawking. While it primarily focuses on Hawking's personal story, it also touches on the nature of black holes and their connection to both relativity and quantum mechanics. It's a nice nod to how Einstein's theory continues to inspire not just physicists, but filmmakers and storytellers as well.
And then there's Star Trek, which has featured relativistic concepts since its inception. Whether it's the warp drive that allows ships to travel faster than light, or the idea of time dilation when traveling at high speeds, Star Trek has always flirted with relativity's mind-bending possibilities. The show's portrayal of time travel, especially in episodes like The City on the Edge of Forever, highlights how sci-fi often draws from relativity to tell stories about paradoxes and alternate realities.
But it's not just movies and TV shows that use relativity to add some drama. The idea of time dilation also pops up in literature, especially in science fiction. In books like The Forever War by Joe Haldeman, the main character experiences time dilation during space travel, which leads to an emotional and cultural disconnect when he returns to Earth after years of fighting an interstellar war. The concept of time moving differently for astronauts has been a popular way to explore the effects of relativity in fictional worlds.
And it's not all about space travel and black holes. Relativity also shows up in more grounded contexts. For instance, the The 2004 film The Butterfly Effect explores the idea of changing small moments in time and how they can lead to drastically different futures. While the film plays with the concept of time travel in a very Hollywood way, it's an indirect nod to how even small changes in time can lead to big consequences, a concept that's deeply rooted in Einstein's ideas.
The reach of relativity in popular culture also touches on something deeper. It represents the possibility that our understanding of reality might not be as fixed as we think. In sci-fi, time travel and the bending of space aren't just plot devices. They're ways to question the very nature of existence, of fate, of free will, and that's what makes relativity such a powerful idea in both science and storytelling.
It's incredible how a theory from over 100 years ago has found its way into such diverse areas of culture. Whether it's the serious, scientifically accurate portrayal of time in Interstellar or the fun, fantastical time travel in Back to the Future, relativity continues to spark our imaginations and challenge how we think about time and space. And who knows, maybe in the future, we'll see even more creative uses of relativity as our understanding of the universe continues to grow.
Now that we've covered the core concepts and mind-bending implications of relativity, let's shift gears a bit and talk about something more surprising: how relativity actually shows up in our everyday world. Sure, we've been discussing black holes and time dilation, but what about the practical applications of these ideas? It turns out, relativity isn't just a cool theoretical concept. It's built into technology and even affects how we navigate the world around us.
Absolutely. One of the most surprising places where relativity shows up is in space travel. For example, astronauts in space are affected by time dilation as they travel at high speeds and experience different gravitational fields. Time moves differently for them compared to people on Earth. If astronauts were to spend a long time traveling through space at high speeds, they'd age more slowly than those who remained on Earth. It's like a real-world version of time travel.
It's crazy to think about, right? But on a more cosmic scale, relativity has huge implications for how we understand the universe. The light we see from distant stars isn't just traveling across empty space. It's influenced by the curvature of space-time itself. This is where we get the phenomenon of gravitational lensing, where light from a distant star is bent around a massive object, like a galaxy. Without general relativity, we wouldn't even have the theoretical framework to make sense of these kinds of observations.
Exactly. Gravitational lensing has become a vital tool for astronomers. By studying how light bends around massive objects, scientists can discover things like black holes and dark matter. It's like using the universe itself as a giant magnifying glass to look deeper into the cosmos. And all of this goes back to Einstein's theory that mass and energy warp space-time around them.
Speaking of black holes, relativity also completely changed how we think about these cosmic objects. For a long time, black holes were just theoretical. But once Einstein's theory set the stage, we started seeing evidence of them through their effects on nearby stars. And in 2019, we even got the first ever image of a black hole's event horizon, which is a huge milestone in astrophysics. Without general relativity, we wouldn't have the tools to study these incredible objects the way we do now.
And it's not just space exploration that benefits from relativity. Even in the world of particle physics, relativity plays a huge role. At places like CERN, where particles are accelerated to near-light speeds, scientists need to account for relativistic effects to ensure the experiments are accurate. Without doing so, the results would be completely off. So, relativity isn't just an abstract concept, it's a real factor in how we study the smallest particles in the universe.
It's incredible, right? A theory that started with an understanding of how space and time work on the largest scales is now crucial for understanding everything from galaxies to subatomic particles. And as we continue to study the universe, relativity remains an essential part of our toolkit.
And then there's how relativity shows up in pop culture. We've seen relativity explored in everything from Back to the Future to Interstellar. These movies take the wild ideas of relativity and turn them into compelling stories about time travel and space exploration. It's amazing how Einstein's theories have inspired such a wide range of creative work.
It's a testament to how deeply Einstein's ideas have permeated not just science, but culture as a whole. Whether it's in movies, books, or TV shows, relativity continues to spark our imaginations and shape the stories we tell about the universe. And who knows? The next big leap in science could very well come from someone inspired by these very ideas.
And that's a wrap on today's episode. We've covered so much, from the foundational ideas of relativity to how it shapes everything from the cosmos to the technology we use every day. It's amazing how Einstein's theories continue to be at the heart of modern science, and we're still making new discoveries thanks to them.
Exactly. Relativity hasn't just stood the test of time, it's still pushing the boundaries of our understanding of the universe. Whether it's helping us study black holes or guiding particle physics experiments, Einstein's theory is just as relevant today as it was over a century ago.
And don't forget, relativity isn't just for physicists. From time travel in sci-fi movies to the GPS system we rely on, relativity impacts all of us, even in ways we might not realize. It's a true testament to the power of groundbreaking ideas to change the way we experience the world.
We hope you enjoyed this deep dive into one of the most profound theories in science. If you did, be sure to like, share, and subscribe so you don't miss any of our future episodes.
And don't forget to check out our Patreon at patreon.com/everythingaboutx for ad-free episodes and more exclusive content. Thanks for joining us, and we'll see you next time. Stay curious.
Everything About X is a product of SynthCast Media. If you enjoyed this program, be sure to check out all the other great shows we produce at synthcastmedia.com. Patrons get ad-free versions of all our episodes, so sign up today by going to patreon.com/everythingaboutx. Our ad partners make this show possible. You can support this program by supporting them.